Okay, let's continue. Okay, so for most of you, this second part of today's lecture would probably be a bit of repetition of what you've seen before. Because I want to introduce the language of propositional logic for those who haven't seen it, and remind the others for what it is, and give the formal background of how we can assign a semantics to the propositional formulae. And then tomorrow and on Wednesday spend time on mostly on the calculator. And I think that is something that you haven't seen before in that depth, and so that's maybe more interesting than today. And today it's sort of to give you some kind of feeling of what is the relation between these languages and practical application in an AI environment. And there are many, many more of those. So knowledge representation, which is the field that I'm also doing my research in, is about how can we devise new languages such as propositional logic or more expressive ones for various kinds of problems in practical domains. As I mentioned last week, I think the most spread around or the most applied representation languages are those for graph structures, which are nowadays used in many of the large search, so web search engines, for example. So the Google Knowledge Graph is the most well known about it at the moment, and the Google Knowledge Graph is based on a formalism where you have objects and classes which you can combine with some relations. So you need a different kind of representation formalism than what we're going to see here. So here, what we just want to talk about is descriptions of those states, for example, in the Wumpus world, where we have a very simple representation of some sensoric information. So is there a breeze or is there no breeze? We don't have anything complicated, qualified statements, for example. So there is a lot of stink here. So there's but we just have Boolean values. So either there is something sensed or it's not sensed. And if you have this kind of information, then this is already a very useful language, because you can model quite some information on this formalism. So what is this formalism? We model propositions, so descriptions of statements of the world, where these statements that we are talking about and that we combine with some operators have the intended semantics of either being true or not. So a proposition is a statement about the world, a content of a sentence, which we always can say, okay, this is a true statement or it's a false statement. The intended semantics of all the statements that we're talking about here in this language are true or false. And as you can imagine, that is in practice very often not the right thing to do, but in many examples it is. So let's see how this works for these languages, for these kind of games such as Schnapsen or the Wumpus world, and that's sort of the goal of this second half of the lecture. So I say all the statements are about truth and false, and these are the propositions in our language. And then we have some operators to combine those propositions, and I will show you how to do that, but most of you have seen that. So, and we're going to use it to represent the facts about the Wumpus world and Schnapsen. And then particularly, most important, tomorrow we're going to see how we can do reasoning over that. So let's start with the syntax. So what are the valid formulae in my language? And as I said, the most important thing in the language is the propositions. So those statements, those atomic statements, which can be either true or false. And if you would define all the all the well-formed sentences in the propositional language, of course, you have to start with all the possible propositions. And usually when you do this definition, you start with a set of countably many symbols that you have to describe your propositions. And that basically means that you have a set where you have whatever way you describe your atomic, the smaller sentences. And this set of atomic propositions is a subset of your legally allowed sentences. Yeah? So that's the starting point, that's the inductive base for your language. And then the next step is an inductive step where you say, whenever I have anything in a language, in my logic, or whenever I have a sentence, then the negation of this sentence is a well-formed sentence of my language. So that's if I have something in the language. So if S is in propositional logic, then the negation of S is also in the propositional language. If I have two sentences in propositional logic, then the new combination of S1 and S2, the conjunction of these two, is also a well-formed formula of the language. And disjunction is a well-formed formula in the language. So in this way, you inductively define all the sentences that are valid in your language. And this is just one variant of defining the syntax of propositional logic. You might have seen different ones. You might have seen ones where different symbols have been used. You might have seen ones where there are brackets. So there are no bracketing here. You might have one where you only start to define the language with negation and I think disjunction, and that's already sufficient to define the whole language, and then all the rest is just abbreviations. But this is a sort of a good overview over one possible definition for the syntax of statements in propositional logic. Now the good thing is with this, you can already write down, I think, all the rules that you need for the Wumpus world. So it's a very simple language. It only allows us to say two statements are true at the same time. One of the two statements or both are true at the same time, or a statement is not true. These are the kind of things that I can say. And the last two would be, if one statement is true, then another must hold. And this one says that both have to be true or false at the same time. So these are the kind of things that we can say in this language. And it's the nice thing about the language that it has very, very nice properties in terms of modeling. It's very simple, and it's the basis for many of the formal systems that are used in practice. And it's interesting enough and good enough to model, for example, the rules and the observations in the Wumpus world, and partially also for Schnapsen. So let's see how we could just use that. And I warn you, it's not a very efficient representation. It's not a small knowledge base that you get even for such a small example, but it works. So the idea is that we have, let's say, different types of observations and facts about the knowledge base, about the game that we can put in our knowledge base. And the set of propositions is just that you say there is a property of the environment plus the position in which this holds. So the set of our propositions would, for example, contain this P1, 2, which would model that in the position 1, 2, there is a pit. And then we could describe our observations as, for the game that we've played before the break, that there is no pit in P1, 1, and then you would just add to your knowledge base the information, not P1, 1, as a way of representing this knowledge about the game. So let's see what we have here. We have information that I was already one step ahead about the description of the game state itself. So here we have the rules of the game. And the rules of the game basically say that if you if you have P of IY, then there must be a pit in IY. And that holds for all the 16 fields of the game. And then we have there the breezes. So B, IJ is true if there is a breeze in IJ. And then basically these would be the observations that we have after being in 1-1, and that is that there is no pit in 1-1, there is no breeze in 1-1, but once I move to 2-1, to the right-hand side, then I realize that there is a breeze in 2-1. So that is a way of representing our observations after the different games, in the steps of the game, into this propositional language. And here we have the rules, which basically say pits cause breezes in adjacent squares, and we can model that in this language easily by saying, now for each individual square of the matrix, we have to do this individually, we have to one by one. So if I say it's easy to do, it doesn't mean it's efficient to do. We basically have to write down that the general rule of breezes mean pits cause breezes in adjacent squares. I have to state for all the different propositional variables, for all the different fields. Yeah. So basically, I have to write for B11 that there must be either a pit in 1-2 or a pit in 2-1. So that was the. So if I have my square here. And I start with this one, 1-1, then if this has a breeze, then there would be a pit here or here. Okay, that's the first thing. And now I have to do this repeat this information for all the squares in the game. So I have to add that if there is a breeze in 2-1, then it's either here or here or here. And then I do the same for P3-1. And for 4-1, and then for the ones in the middle, I have to do the 4 around. Yeah. So if I have a breeze in 2-2, then it is either in. So that would be now this one. It would be either here. So either a pit in 2-1 or in 1-2. This one or 2-1 or this one. Yeah, so it's very easy, but it's rather tedious to write down all of those statements about the environment. But that's something that you would normally do automatically. You write a script that does all these statements for you. And then basically you have a number of formulae that model the rule of the game, namely that for every for every square where I have a breeze, one of the adjacent must be a pit. Okay, so that's this part of the game. And then you have to do the same for all the different rules that you have in the game. So what was the other one? If there is a smell, then in one of the adjacent fields must be the Wumpus. And then you have to write down, if smell 1-1, then Wumpus. Because of course the idea is that the computer program that we want to play the game later doesn't know anything. So it doesn't. We know that P11 that we don't maybe have to write all those rules out explicitly. But the idea is that we have generically now represented our knowledge base in this form, and then whatever observations we have, the rules just stay the same, and the reasoning can be applied in the same way. So the same is now we have to do for our cards. So the way this is implemented in the game engine, unless I'm very mistaken, is that we have those 19 cards numbers from 0 to 19 in the game engine. And now if you want to do reasoning over them, you have to assign the right values to them. So basically what we have to say is that card number 0 is an ace. That's one possibility. So our propositions that we would have in our language would just be assigning all possible values to the cards. So we could say that the card number 0 could be a 10 of clubs. Okay, but that would be a possible one. But as we know how the game is implemented, we can just state in the beginning that card number 0 has the property that it's a clubs card. So we start with the with the basic proposition that what do we know about those cards, and then if we want to say what are all the aces, for example, then we would model this as ace 0 and 0 is an ace, and in this way we can build a knowledge base that implements all the rules that we have of the game in the same way as we do with the Wumpus.
Yeah. When programming something with playing cards, it's easier to use index and do all the other stuff like deriving its suit differently from that, or is it also an idea to have every card be represented by a tuple which holds the rank and suit? Or is that not?
So I think that's a very good question. The question was in how much you want to. Okay, how do I phrase this back? So have indices in which you sort of do the bookkeeping for what kind of properties the cards have. And I think what we must distinguish is an efficient way of modeling the different game situations and also the strategies that you could have. And I believe that in some of the bots that we have, the bully bot, for example, you check whether something is an ace or a high card in the code directly. So you check is something an ace by running a procedure or a method from the game engine. What we want to achieve here is that we have some explicit layer of logical reasoning, so that we could define a concept which says, okay, these are the aces, and these are the 10s, and these are the high cards. And a high card is a 10 or an 11. And you make this on a very high-level declarative statement. And then we could decide, or we could discuss whether a 10 is a high card or a not. But then it's something which we on a human level can relate to. And this is impossible if you do that somewhere hidden in a code. So nothing what we do here with an explicit logical representation is something you couldn't do in the programming on the programmatic level, but it's far more easy to lose control, and it's far more difficult to really talk about the more conceptual level of your decision. So in a way, oh, yes, nice. Why does it always try to do this during lectures? I must have an algorithm to do that. So I think what is really important here is that we try to get the knowledge that is involved in those games, that we try to make this explicit, so that we can explicitly talk about it with humans and explicitly reason over it and make decisions on that point. Everything could also be done on the programmatic level, but we try to really lift it up here to a declarative level. That's the idea. So let's see how this is sort of turned into a formal semantics, the formal meaning of these formulae. And the idea is basically based on Polish philosopher Alfred Tarski in the 40s, 50s. He developed the system, and the basis of this was that people tried to assign truth to statements, and it turned out that truth is horribly complicated, so we don't really know what it is. And logicians and computer scientists in particular are usually quite good at pragmatic solutions. So whenever we can't make a principled decision on what does it mean, truth, then we come up with an operationalization of it. And basically what Tarski did was this operationalizing of the notion of truth. And what he basically said, we don't bother about, or we don't know what it is for something to be really truth. We don't do metaphysics. But what we can always do is to define truth in terms of some problem, in terms of a meta language. So we have a mathematics system in which we can ground our problem, and then we can define the notion of truth or all the related semantic notions with respect to these meta languages. And based on this idea, he came up with the models theory, where you basically say we look at all the possible formal interpretations of the world given a certain formal meta system, and on the basis of something being true or not in those possible models, we can now define our notions of something following from the knowledge base, yes or no. And the idea is that these models, so you choose a space of interpretations, and then the models are those interpretations within all the possible interpretations that make your knowledge base, that hold with respect to the properties of the knowledge base. So if you think back to this algebraic question about the arithmetic, the choice of our possible worlds are the assignments of values in our of the variable values. So you saw these statements, these arithmetic formulae, and then you can choose to have natural number interpretations. So that's one formal system in which you interpret those, and based on the choice, you know which of those interpretations are correct with respect to the statements you have. And on the basis of this choice, you can define a notion of correctness or entailment, and that's then generic for all the different interpretations that you can find and different formal systems. So a model of a sentence is one that a choice of the possible values for all the variables and propositions, in our case here, of the language, that adhere to all the criteria of our knowledge base. Yeah? And then we can define all the models that do this. So, for example, we had on the previous slide, here in this one, we have not P11. We know that there is no pit in 1-1. So basically, a model for this, only this one statement, if it was in isolation, would be that P11 has to be false. Yeah, so I can only choose P11 to be false if I want to satisfy this constraint in my knowledge base. So basically, I have this one formula, not P11, and that defines my model in this case, because it's only one where I choose non-P11 to be false. Sorry, if P11 to be false, that makes this formula true. And now what the formal semantics does is that a formula becomes true with respect to a knowledge base, or follows from a knowledge base, if it is true in all the models of this knowledge base. Yeah. So we have this then this notion of a model or satisfying a certain formula, and we of course need to bring this down to all the complex constructed composite formula. So basically, we know that if we have a proposition, then this has to be true. So the proposition 1, 2 is either true or false. So I have a choice of assigning two different values. And then I can calculate whether the complex formula is true or false by applying those rules. And they basically say that if not S is true, then S must be false, and vice versa. Yeah? If S1 is true and S2, so if this formula S1 and S2 must be true, then both of those individually must be true. This junction is either of the two must be true. Implication means that either the implicant is false, or if it is true, then the right-hand side must be true. Yeah? And you have seen those definitions of using some truth tables, and this is exactly the same as was defined with the truth tables. It's just the exact definition of how do you calculate the composite value of these more complex formula. Yeah. So if you have a formula such as this one, you can evaluate the value of the complex formula by this recursive process by just evaluating what is the value of the propositions. And in this case, we have, for example, assigned truth values to the propositions, like P12 is true, P22 is true, and P31 is false. And then I can calculate the value under the choice of this assignment. So I can now check whether this is a model, this variable assignment for this formula, and I can check that the left-hand side is false, because we know that it's true. The right-hand side is false, so that's P22 is and P31 is true. So the order is incorrect here. So this one is true, and false and true is false. So basically, this formula is not satisfied by this variable assignment. So this choice of variables up here is not a model for this formula. We can now calculate for complex formula. We can calculate recursively the value for any formula in the language of propositional logic. So how does it help us? We can now check for every possible value in our game whether a certain property holds. So let's now look only at the bottom 5 part of the game. And so the situation is that we have detected nothing in 1.1. We've moved to 2.1, and we've noticed the breeze. Yeah? And now we are going to use the reasoning over the model that I've talked about in the last slide in order to determine whether or not there are pits in any of those fields with a question mark. And so basically the question is the proposition P21 true, or is it can I show it's the other way around? Can I show that the proposition not P2 is true? Because if I can show that not P is true, then I know that there is no pit, and I can move there safely. So basically, I could define a proposition which is safe to 1 if there is no pit and no Wumpus and so forth. Now, all I want to show now is that there is no pit and no pit here. We'll restrict really to this simple example. There is no pit here and so forth. So I have these 3 variables, namely pit to 1, pit to 2, or pit 1, 3. And what are the possible combinations of there being a pit or not being a pit? Yeah? And these are the positions, the possible positions of somewhere being a pit in this game. Only for the left-hand corner, remember, we only look at those 5 fields, yeah? Given the observations that we had on the last slide. So there's a breeze. And then remember, it's only about those 3 fields now, whether they contain a pit or not. So the pit, there could be 1 pit here, there could be 1 pit here, or there could be 1 pit here. Yeah, there could be no pit at all. And we're now checking in a minute whether those models, those interpretations adhere to our knowledge base or not. There are 2 pits here, there are 3 pits here, there are 2 pits here, there are 2 pits here. So these are all the possible combinations of whether there are pits in these 3 squares or not. Yeah? Sorry, I said that, but I shouldn't have said. So they are not models, they are possible interpretations. Yeah? And we're now looking at which of those 8 interpretations are models for our knowledge base. So now that's exactly the next question. Which of those 8 interpretations are models for our knowledge base? Yeah? So which of them, in other words, are consistent with the knowledge that we've modeled on the slide before? And basically what we've modeled is the rule that if there is a breeze, one of the adjacent ones has to have a pit. So we have the breeze here, so one of the adjacent ones needs to have a pit. So it should be clear that this one is not a model. Yeah, it's an interpretation, but it's not a model. So which are the ones that are models? Those three. Yeah? Because this one has a breeze, and one of the adjacent squares has a pit. One of them, nothing says that not both can have a pit. This one has an adjacent one, and this one has an adjacent one. We had already ruled out that this one can't have a pit, so that's why we don't consider it. It's about those three, and those three of the interpretations of the variable pit in to 1, pit into 2, or pit in 1, 3. Only those three are consistent with the knowledge that we have about the game engine, the rule and the observations. And the others are not. Yeah? So the knowledge base is Wumpus world plus the observations, and these are the three models of this knowledge base. And now we can use this notion of model for a knowledge base in order to define all the important semantic notions. And the most important one is the notion of entailment. I sort of bored the people, the AI students in knowledge and data with this for quite some time. But this is a very important logical notion that's broadly applicable in almost all the logical systems that you have. And that is basically the notion that a knowledge base entails a proposition, a formula in general. If this proposition is true in all if this proposition sentence is true in all the models. So in all the worlds that are consistent with the knowledge base. And we later define some other notions on satisfiability and so forth on the notion of entailment. So entailment is the most important one here, and it is just this definition, and you just have to sort of learn it by heart. It's a formula is entailed by a knowledge base if it holds in all the models. So what does it mean now with our example? The question is, does the knowledge base entail the question, the proposition that A22 is safe? And what does A22 is safe mean? That there is no pit in this case? Yeah. So can we prove logically that there is no pit in 1, 2, which is this one, I think. Yeah. And how do we do that? We look at all the models of the knowledge base, basically those three states, and we just check for all of those models whether there is a pit or not. And here is no pit, here is no pit, here is no pit. So basically we have now proven that 1, 2 is safe, there's no pit, so that the agent can move there. Yeah. There is another way of looking into that. Yeah, sorry.
So in a given state, so for example here, it's like 8 are the all total sets of states you can go, and the 3 on the left are the model.
Yes.
Selected, right?
Yes. And what you basically can do in order to check automatically whether your propositional sentence is entailed is that you look at all the models for 1, 2, and the models for 1, 2, where this one is true, is safe, are all the places where there is no pit in 1, 2. So the yellow one, this is alpha 2. These are the models for 1, 2 is safe. So the yellow line determines all those 4 statements where there is no pit in 1, 2. So here we have a pit, here we have a pit, here we have a pit. So if this set of models for alpha 1 is a superset of the set of models for the knowledge base, then this also means entailment. Yeah? So if you have another example where, for example, we want to show that 2, 2 is safe, yeah? So then we check which are the models for 2, 2 is safe, and these are the models where there is here is no pit. In all those 4, there is no pit. And now we check whether that's a superset of the knowledge of the models for the knowledge base, and if not, because we have also models which are possible interpretations with respect to the rules of our game, in which there is a pit in 2, 2, So basically, this means that we cannot show that tutu is safe. So the not a pit in tutu follows from the knowledge base is not true. So we cannot show entailment. Yeah. And now the important thing is that we have algorithms for calculating entailment in a very efficient way. So if we model the rules of the game in propositional logic, if we model the observations in propositional logic, then we can calculate the notion of safeness, for example, as not having a pit and not having a breeze as a propositional formula. And we can just check whether this formula is entailed given our knowledge base based on the rules of the game plus the observations. And that's basically all that is. And the next days we are going to look into algorithms for proving entailment or disproving entailment. And basically what in the real literature for logic, when you follow a logic class, an advanced logic class, there are many interesting properties about the languages. For example, the notion of satisfiability or validity, and they are all related to this notion of models. But for example, so this is the one that I showed before. The notion of entailment is if a formula, a sentence alpha is true in all the models of the knowledge base, then it's entailed. A sentence is valid if it's true in all the models in all possible models. A sentence is satisfiable if it has a model. It's unsatisfiable if it is true in no model, and so forth. So these are classical notions of logic that you will study in the logic course, but we are really trying to bring this to practice, and the only two notions that are relevant for us is entailment and satisfiability. And unsatisfiability, we're looking into that tomorrow and relate the two things, because we want to look at algorithms that prove entailment automatically and algorithms that prove satisfiability, and they are very strongly related. So what we also want to do now is to look into different ways of representing the rules of the Schnapsen engine, the Schnapsen game, and that is basically part of the milestone 3. So there you can run a satisfiability solver that calculates automatically whether things are satisfiable, and that allows you to do entailment, and I'll explain tomorrow how that works. And basically you can then see whether you can check whether a certain property holds for your states, so that you can apply the reason by reasoning, and then whether it's a good choice according to a certain strategy following the logical reasoning, and that's what we're going to look into tomorrow as well. And I think that was all I want to say, so we are 5 minutes early. That's good news. We'll see you tomorrow.